Так оно запущено. Как выглядит запущено? Давайте на всякий случай проверим. У нас, кажется, каждая пара начинается. Проверим. На всякий случай проверим.
Да, пошло.
Пошло? Okay, so let's start. Today I would like to take another step towards the proof of the prime number theorem. Let me remind you what is the goal, like a local goal for several lectures is to prove the following relation. Phi of x is asymptotic to x over logarithm of x. And we have discussed that this is actually equivalent to psi of x being asymptotic to x, where psi of x is the sum over all n less than or equal to x, lambda von Mangold function. And what I'm going to do today is I'm going to start with the motivation. Why do we need to study the properties of zeros of zeta function? I mean, what precise statements do we need? And then we are going to prove the explicit formula for psi of x, and maybe then we will deduce some consequences of the Riemann hypothesis. Okay, so first of all, Perron's theorem. This will be a theorem that relates sum over all n less than or equal to x a sub n, where a sub n is some interesting sequence. Well, we will relate this summitary function to the properties of the Dirichlet series a sub n.
Извиняюсь, запись пошла?
Запись?
Да.
Да, автомат, по-моему, сохраняется.
А, ты проверял, все. Все, я это и хотел
Отдельно
узнать.
ничего не нужно делать.
Все, ничего не нужно, просто я как раз хотел узнать,
Okay.
идет или нет.
So we are going to relate properties of summitary function to the properties of of the Dirichlet series. Of course, we are going to need to assume something about the properties of our sequence to establish an understandable relation between these two quantities. So let me state the main theorem, and then we're going to discuss. So theorem 1 for today, which is Perron's theorem, will be as follows. Suppose that a sub n is some sequence of complex numbers, and let b be greater than 1. Maybe we'll also assume that our quantity t is greater than or equal to 2. I'm not sure if we will need this, but still. Okay, b is greater than 1, t is greater than or equal to 2. Capital A.
What is t?
T is some real number. It is unrelated to am. That's actually the point. So a of x will be increasing function, maybe non-decreasing, but okay, increasing function such that absolute value of am is at most a of n. You see, our sequence can be very much non-monotonic. It may be something like lambda of n. It is sometimes 0, sometimes non-zero, sometimes something else. Okay, so absolute value of n will be bounded by our function, and assume also that we have the following bound, that for sigma tending to 1, we have the following. So assume that the Dirichlet series with an replaced by absolute values at the point sigma. So we replaced our arbitrary sequence of complex numbers by a positive sequence, non-negative sequence. Suppose that we have the following: that this is this grows at most like 1 over sigma minus 1 to the power alpha. Alpha, say, is greater than or equal to 0. Okay? So we have these conditions.
Сейчас. Там, ага. А альфа мы где определили? Альфа мы взяли просто как...
Alpha is also some parameter. So we have how many parameters here? So we have b and t, which did not appear in these conditions. We have increasing function, which bounds our sequence of coefficients, and we also have the following bound for the Dirichlet series with absolute values. Then, and let me conveniently continue on the next page. Then we have, then say for any x of the form n plus 1/2. So, of course, to understand the behavior of such a summatory function, it's enough to understand its behavior at half integers, right? For some very simple technical reasons, it will be more convenient to consider half integral values of x. We have sum over all n less than or equal to x, a sub n, is equal to 1 over 2 pi I. Then we have integral from b minus it to b plus it, f of s, x to the s over s ds. Here f of s is of course sum a sub n over n to the s. So this sum will be related to this integral, and we also have some error term here. Let me write down the error term. The error term would be x to the b divided by t b minus 1 to the power alpha plus 2 to the b x a of double x logarithm of x divided by t. Okay. If I wrote everything correctly, yeah. So let's discuss what does this mean. So it turns out that.
Может, нескромный вопрос.
Ага.
Как люди вообще до этого дошли?
Ну, можно сказать, что это просто такое общее утверждение. Как бы на самом деле можно каждый раз передоказывать что-то похожее, но когда вы докажете что-то похожее 10 раз подряд, вы поймете, что на самом деле удобно написать что-то такое. Okay, so this is a very general statement that allows one to relate the properties of summatory function to the Dirichlet series. One can also write down this thing the other way around when you express the Dirichlet series in terms of summatory function, but this is an easy exercise and this is not that easy. Well, what you can notice, the first thing you can notice here is that if t goes to plus infinity, then your error term vanishes, right? So if you set t to be plus infinity, you get exact identity. This is, of course, not a coincidence because, well, this is related to properties of Mellin transform. This is basically an inversion formula for Mellin transform. If you consider this function, and I think you should also change a little bit of variables, so you should replace x by 1 over x and then take the Mellin transform. You will get precisely the Dirichlet series. For the sake of completeness, let me tell you. Mellin transform is defined as follows. Suppose you have some function f from f is not okay in this context. Sorry, g from non-negative real numbers to complex numbers, then you can define Mellin transform of g as follows. This is an integral from 0 to plus infinity g of x multiplied by x to the power s minus 1 dx. So some of you might notice that we already seen some integrals of this form, right? In fact, gamma function is of course a Mellin transform of e to the power minus x, right? Also, Mellin transform can be interpreted as a Fourier transform on the group of non-negative real numbers with respect to multiplication. So this is basically a multiplicative Fourier transform, and this also explains the appearance of s to the minus to s minus 1 here, because x to s minus 1 dx is of course equal to x to the s dx over x, and this is an invariant measure on this group. Okay, and Mellin transform can be inverted. You can prove that g of x is actually equal to 1 over 2 pi I integral from c minus I infinity to c plus I infinity g tilde of s x to the minus s ds. And from this formula you can easily deduce what is the function and what is the Mellin transform here. You should consider some step function, and then
from where do we get this c?
C, well, this is a technical thing here. If you assume that your Mellin transform is say holomorphic for real part of S greater than say C minus epsilon, then you can write such a formula. This is Mellin inversion formula. Maybe not greater than epsilon, but less than epsilon. Okay, it's one should look at the precise statement of Mellin inversion. So here, this formula is basically a Mellin inversion formula for certain function, but it is also a truncated Mellin inversion formula. Instead of integrating over the whole line, you take a small, or maybe not so small, interval of this line and integrate among this interval. Okay? Усеченная. Ну, в смысле, вот у нас есть бесконечная версия, а мы хотим вместо бесконечности что-нибудь поставить. Конечное. Угу. Чтобы не было бесконечных интегралов, которые непонятно как контролировать.
So in the inverse, there's x to the power of minus s.
Yeah, and here x to the power s. Okay, so let's compute the integral maybe. So if you define g of x to be something like sum over all n less than or equal to 1 over x an, and you can define g of 0 to be 0 or something like this, then the Mellin transform of g is equal to integral from 0 to plus infinity g of x to s minus 1 dx, right? And then this will be sum over all n, and then your an appears in g of x if x is what? If x is at most 1 over n, right? Mm-hmm. So you get integral from 0 to 1 over n, x to s minus 1 dx, correct?
Mm-hmm.
And this integral is, of course, equal to 1 over n to the s multiplied by s. So the Mellin transform of this function is equal to f of s divided by s. Okay? So this is the motivation. You can prove Mellin inversion formula, and then you can notice that your function, your Dirichlet series, is a Mellin transform up to some obvious obvious changes of variables and multiplications. And then you would like to prove the truncated version of your formula. Okay, so let's prove it. I think that's motivation enough, right? Of course, to prove it, we are going to need some useful lemma. Lemma 1 is kind of a building block of our formula. It will look as follows. Suppose that a is greater than 0 and t is also greater than 0 and b is also greater than 0. Then the integral 1 over 2 pi I integral from b minus it to b plus it a to the s divided by s ds is equal to the following. So it is equal to 1 plus big O of a to the b divided by t logarithm of a if a is greater than 1. And it is equal to the same error term, but of course with minus logarithm, so I'll write absolute value of logarithm when a is less than 1. Okay? And you can probably guess what is the main term if a is equal to 1. Any guesses? Of course not. So if a is greater than 1, you get 1. Mm-hmm. If a is less than 1, you get 0, right? 0 plus something. Mm-hmm. So what do you get if a is equal to 1? Of course, if a is equal to 1, you get 1/2. But a equal to 1 will not be in our cases here, so I will just skip it. So let's prove lemma 1. And I'll prove just one part of it when a is greater than 1. And the second part will be left to the listeners. Okay? So suppose that a is greater than 1, and let us take a very large u greater than 0. Now we integrate our function over the following interval from b minus it to b plus it. And the direction of integration is like this. Then I would like to make this interval a closed contour. To do so, I'll go very far to the left and get minus u plus it. Then I have vertical segment, and then I have minus u minus it. Okay? And let's denote this contour by c. What is the integral 1 over 2 pi I, integral over c, a to the s over s ds? Can someone please tell me?
Which of the...
Yeah, of course. This is equal to the residue of our function at s equals 0. And what is the residue?
A to the power of s divided by s. Yes.
Yeah, so we have a to the s divided by s, and we want a residue when s is equal to 0. What is the value of this residue? 1. The value of this residue is just 1, right? Because we multiply by s, and then we set s goes to 0. You get a to the 0, which is 1. Okay? Now, our integral is equal to the integral we wanted from b minus it to b plus it. Then we have two integrals b, so we have plus minus b plus minus it minus u plus minus it, right? And then we have the integral from minus u minus it to minus u, the other way around, from minus u plus it to minus u minus it. Right? So what we need to prove is our estimate like this for these three integrals. The upper one, the lower one, and the vertical one. So, of course, the upper and lower integrals are complex conjugates, right? So they're conjugated to one another. So we need to estimate just one of them. Let us estimate the vertical integral. Integral from, say, b plus it to minus u minus it, a to the s over s ds. How can we estimate this integral? Well, this is obviously bounded by 1 over t, which is the lower bound for absolute value on the bottom, right? Integral from minus u to b, a to the sigma, d sigma. Correct?
Почему там интегрируем от b плюс it до минус u минус it?
Sorry. Plus it, of course. No diagonal terms. On the vertical, on the horizontal and vertical. Okay, so this integral is easily bounded by a to the b divided by t logarithm of a, right? This is obvious. Okay, now
Wait.
what?
Wait a second.
So, можно посмотреть.
Сейчас, а можно подробнее переход к сигма?
So we integrate from b plus it to
куда у
minus
нас-
u plus it.
Да.
Then you set s to be sigma plus it, and sigma runs from minus u to b, right? And
сейчас,
ds on our interval is equal to d sigma.
Сейчас, еще раз. У нас сигма это b.
S равно sigma плюс it.
Ага, все, понял, спасибо.
Ну и все. Then we integrate, and we get a to the b minus a to the minus u divided by log a. So a to the minus u can be ignored, and we get a to the b over t log a. Okay, and this last integral, vertical one, obviously goes to 0, right? Because, well, it is bounded by let me write it here, minus u plus it minus u minus it a to the s over s ds. And it is very roughly bounded by a to the minus u divided by, say, u multiplied by t. Correct? And then you send u to plus infinity, and you get something going to 0, because a is greater than 1. Okay? This should work. Okay, so we proved this part. To prove this part, you need to go not to the left, but to the right. And this will be an exercise for the listeners. Okay? So we are going to use this...
Еще раз, можно повторить оценку на этот интеграл?
На который?
Который вот мы последний выписали, да.
Вот этот. So, the numerator... sorry, 2. The numerator is at most a to the minus u. The denominator is at least u. And the length is double t. What I need is that if you send u to plus infinity, you get 0. Nothing else. Okay, so now we are going to apply this lemma to prove our theorem. Exercise. Упражнение. В единице не получится вот этот аргумент. Правда же? Вернее, получится, конечно. В единице получится этот аргумент, я согласен. В единице вот этот интеграл разойдется. Ну вот. Estimation of what? Of the vertical, horizontal integral, or what? This one?
Yes.
So S...
Why it's not T, the T, I think.
Absolute value of S is at least T. Right?
Okay.
That's it. It's not very it's not very sharp estimate. It's simple, and it is the main kind of upside of this estimation. Okay. Interesting. Okay. So let us deduce our theorem from the lemma. So take our integral 1 over 2 pi I integral from b minus it to b plus it f of s x to the s over s ds. I will change the order of summation and integration, which is possible because the corresponding sum is absolutely and uniformly convergent due to our assumptions. So this is equal to the sum over all n, a sub n, multiplied by 1 over 2 pi I, integral from b minus it to b plus it, and then what do we get inside the integral? F of s is sum an divided by n to the s. So we get x to the s divided by s and also divided by n to the s, right? So we get x over n to the s ds over s. Correct? And this integral is exactly the integral appearing in lemma 1. So this is equal to sum over all n, an, and then I'll write indicator function of the following inequality, sorry. It is indicator of x over n being greater than 1. So if x over n is greater than 1, then we get 1, and then if x over n is less than 1, we get 0, right? And then we have the same error term for every summand. The same error term will be x to the b divided by n to the b t absolute value of logarithm of x over n, right? This is by our lemma. So now we already have the much needed summand sum over all n less than or equal to x a n, because x over n is greater than 1 if and only if n is at most x, right? So this is equal to sum over all n less than or equal to x a n plus some error term. And now the goal is to estimate r. So let's do it. What can we do? So we get sum over all n, big O of absolute value of an multiplied by x to the b divided by n to the b t absolute value of logarithm of x over n.
Можно вопрос? Почему
Yes.
сам сумма n меньше либо равно x?
When do we have x over n greater than 1?
Да.
It is when n is less than x, right?
Так, все.
That's it. Okay, so R is this sum, and so it is bounded by the sum of these terms, right? Do we have a problem with this sum? Can we estimate it directly or not? So, of course, we can estimate the sum somehow, but we have a problem in the denominator. If n is close to x, then logarithm of x over n is close to 0, and we get something large, right? So let us estimate this by two different summands. The first one will correspond to n being close to x in multiplicative sense. So at most double x and at least x over 2, say. And the other will be sum over all n far from x. Okay? So R1 will be sum over all n greater than or equal to x over 2 and at most double x. And this will be absolute value of an x to the b divided by n to the b t logarithm of x over n. And R2 is the same sum but outside this interval. Let's denote this n inside G, and then we will write n is outside of G. R2 is the same, but n is not in G. So this sum is, of course, more interesting to estimate, in my opinion. Okay, so let us write n to be x plus h. Then h is half integer, right? And h is absolute value of h is at least 1/2, and at most say x, right? So this is because n is an integer and x is a half integer.
1/2 x, probably.
What?
Ah,
No. If n is equal to double x, then you get x. Next, absolute value of logarithm of x over n is equal to absolute value of logarithm of x over x plus h. which is absolute value of logarithm of 1 plus h over x, which is of order at most h over x, right? Sorry, not at most is bad. At least h over x, right?
Half integer. It means it's a multiple of. It's an integer multiple of 1.
What? No, half integer, I mean it is integer plus 1/2. Okay? Now, what do we get from this?
Там, возможно, не x, а n должно быть
Uh,
в знаменателях.
x. Смотрите, я перевернул. Logarithm
Да,
of
спасибо.
x over x plus h is minus logarithm of x plus h over x. And then I'll write h over x. Okay? Does this work? I hope so. Okay, so absolute value of an.
Еще раз можете показать по ГОСТу? Ага. Алгоритм.
Here?
Спасибо.
So absolute value of an. So suppose that n is from our interval. Absolute value of an, x to the b, n to the b, t, absolute value of logarithm of x over n. What is this? This is bounded by the following. So x to the b over n to the b is at most 2 to the b, right? So it is at most 2 to the b. Then you get a of double x, which is the bound for absolute value of an. And then you get t, and then you get h over x. Correct? This is the bound for logarithm. So you get 2 to the b, a of 2x, then x, and then th. I think absolute value of h. Sorry, h can be negative. So now we get that R1 is at most 2 to the b x a of 2x divided by t, sum over all h from 1/2 to x, 1 over absolute value of h. How can we estimate the sum? Any suggestions? Sum 1 over h. Logarithm of x, right? So this is at most 2 to the b x a of 2x log x divided by t. That's it. This is exactly the first term, or the second term, sorry, of our estimate. Now for R2. R2 is what? Well, for R2, this logarithm is bounded from below, right? If n is far from x. So it's bounded by log 2. So R2 is at most the following sum. Sum over all n, not just from the interval. Absolute value of an, then x to the b, n to the b in the denominator, t, and that's it, right? Logarithm disappears. This is because logarithm is bounded from below by a constant. So this is almost exactly the other sum from our theorem. This is...
We estimate R2 the same way we estimated R1?
No. For R1, our logarithm can be quite small, but we can estimate how small it is. And for R2, we just ignore the logarithm. The logarithm is at least log 2. Okay?
But in R1, we use sum over n, but maybe.
So if you get the larger sum, then you get the bound from above, right?
No, I mean the same edge when you run through ON, maybe you take 2 times.
So what? I care about this up to a constant, right? Okay, so this sum is at most x to the b divided by t, and then by b minus 1 to the alpha. This is because we get absolute value of an divided by n to the b, and this sum, we supposed that we have some estimate for it, right? Let me show you the statement of our theorem. Here it is, right? And so we get exactly the error term we wanted, x to the b over t, b minus 1 to the alpha. And today I would like to apply this theorem to prove the so-called explicit formula for psi of x. Okay? Let me give you a simple exercise. A simple exercise would be prove that, say, sum over all n less than or equal to x, t tau of n squared is equal to, is, say, what can we do here? It is asymptotic to what? It is asymptotic to some constant multiplied by x multiplied by logarithm of x cubed. Prove this estimate using our method. One can actually do much better than this. Okay, so let's move to the second part of the lecture. Here I will discuss the explicit formula. What is the explicit formula and why do we care? So explicit formula is a way to relate Chebyshev psi function, which is the sum of von Mangold function, to zeros of zeta function. And so let me get the precise statement here. Theorem to explicit formula. We are going to...
Сейчас, мы, получается, уже вот...
Доказали, да.
То есть мы, получается, оценили R1, R2.
Угу, и дальше собрали их в одну сумму.
Все, да, понятно, откуда все вылезло. Все.
Можно вопрос? А вот у нас в теореме было предположение, что сигма должно стремиться к единице. Но только больше единицы.
Окей. Ну, правильно, да. Sorry. Let's assume here that b is also bounded from above by some constant. So the moral here is don't take b too large. Okay? If b is bounded by some constant, then of course this term will not ruin anything, right? Because if b is very large, then you have some problems here. You have too good of an estimate. But if b is bounded from above by a constant, then this does not
А пока мы не сформулировали следующую теорему, можно попросить окошко открыть?
Да, с удовольствием. Ого.
Там очень редко говорит.
Ничего, нормально.
Там есть эта крепилка.
Там есть крепление.
Вот так. Давайте так пойдемся, да? Okay, so what is the explicit formula? And once again, why do we care? Explicit formula is the following statement. Let x, we will assume that x is a half integer once again, but this will not affect much of our further considerations. So let x be a half integer, suppose it is at least t, and t is, say, at least 2. Then we have the following formula. Psi of x, which is, to remind you all, sum over all n less than or equal to x lambda of n, is equal to the following nice quantity. It is x minus sum over all rho, such that absolute value of imaginary part of rho is at most t, x to the rho divided by rho plus big O of x log squared of x divided by t. And what is rho here? Rho is a non-trivial 0 of zeta of s. So it turns out there is a nice simple formula for psi function in terms of non-trivial zeros of zeta. So the only problem of estimating with estimating psi of x minus x lies in the non-trivial zeros of zeta. There are proofs of the prime number theorem that avoid the explicit formula, and as far as I know, there was some kind of an argument between the famous mathematicians at the beginning of 20th century if it is really necessary to prove the explicit formula to prove the prime number theorem, but after all of the kind of bickering, they decided that actually the proof with explicit formula is the simplest one. All the other proofs are a little bit less natural and a little bit more artificial. Okay?
So the prime number theorem is to which term?
What?
To which term of your
What do you mean?
I mean,
If you want to prove prime number theorem, then the most natural way to do it is to prove the explicit formula, then prove some results about zeros of zeta, which we will not discuss today, and then obtain your result.
oh, I mean the prime number theorem. You mean to which?
Even just to prove that psi of x is asymptotic to x. All other ways to prove it are a little bit less natural, but we will discuss one of the ways on the seminar. Okay? Okay, so also, what is a non-trivial zero of zeta? Let me remind you all. So we proved the functional equation for the Riemann zeta function, and we established that there are zeros of zeta to the left of the critical strip. And what are the zeros of zeta to the left of the critical strip?
Minus 2, minus 4.
Minus 2, minus 4, and so on. So here, minus 2, then minus 4, and so on. These are called trivial zeros. And all the non-trivial zeros live here in the critical strip. Okay, so to prove this second theorem, I am going to use some complex analytic tools. So first, I would like to tell you about the Weierstrass factorization theorem. I will state the most simple, relevant way to state this theorem. So this will be a lemma, but without a number, because I will not prove it. This is a different discussion. So suppose that big F of Z is an entire function of order alpha less than 2, not less than 1. What I mean is that absolute value of f of z is at most exponent of some constant dependent on epsilon, absolute value of z to the power alpha plus epsilon, say plus 1. Okay? So basically, I know that we have a function which is holomorphic in the whole complex plane, and its logarithm grows at most like absolute value of z to the power alpha. Okay? So it is not, it does not grow very fast.
Сейчас вопрос. C эпсилон это кто?
Константа, которая зависит от эпсилона.
I'm sorry, but what is the order of an entire function?
Once again, the order of an entire function is the infimum of all alpha, such that we have such an inequality. So what I said here is that if you take logarithm of absolute value of f, then it grows at most like absolute value of z to the power alpha plus epsilon.
This
right?
is the definition of an order.
This is the definition.
Okay.
Yeah.
I thought this is the lemma.
Okay, so we have this bound, and assume also that f of 0 is not equal to 0. Okay?
Простите, а вот при этом условии бывает, что функция растет быстрее, по каким-то последовательностям быстрее, чем модуль z в степени альфа? Ну, на константу там.
То есть? Да, конечно, бывает. Разумеется. Не, бывает, конечно, бывает. Можете попробовать пример.
А, это...
Не, экспонент все прекрасно. Вопрос не в этом был. The question was, can it grow, can this epsilon be removed? The answer is no. You should not remove an epsilon. Okay? So, and f of 0 is not equal to 0. Then we have the following formula. F of z is equal to exponent of a plus bz for some a and b multiplied by and the product over multiplied by the product over all w 1 minus z over w e to the z over w, where the product what is the product? What is the w here? Any guesses? Of course. Runs over zeros of f with multiplicity. So if you have a double zero, you should take your zero twice. Okay? And also one can prove that this product is absolutely convergent. Actually, one can prove that the sum over all w, 1 over w squared, is less than infinity. Okay, so if you have a function that does not grow too much, then it is equal to some simple exponent multiplied by the product of all zeros. Okay? For example, sine of pi z divided by pi z, which is of course an entire function, is equal to the product over all n, 1 minus z squared over n squared. This is a very, very particular case of this Weierstrass factorization theorem. Okay? So, we are going to apply this lemma to some nice function. We are going to define psi of s to be, I don't remember the classical convention, but this should be it, half of s times s minus 1, pi to half of s, gamma of half of s, zeta of s. This will be the psi function. I also defined psi function at the previous lecture, but without these factors. So this should be psi1. Okay, this psi function satisfies some nice properties. First of all, psi1 is entire. Second of all, psi1 of s is equal to psi1 of 1 minus s. This is the functional equation we dealt with at the previous lecture, right?
У нас уже доказательство леммы пошло по итогу.
No, we are not going to discuss the lemma. Lemma is not numbered, so it will the proof will not be discussed.
Она
Okay?
называется
Weierstrass factorization theorem.
Blah, 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 is very strange. The
What is strange?
the sum of squares are convergent.
Of
The
course.
sum of squares of zeros convergent.
Sum of inverses of squares of zeros. It is not very strange. It just means that we do not have many zeros.
Есть еще там π в степени минус s пополам и гамма от s
At s пополам, z at s. So we proved that this function satisfies the following functional equation. And we also know, please check it, that psi of 0 is non-zero. This is because we multiply by s here, but it cancels out with the pole of gamma. And the fourth statement is that absolute value of psi1 of s is at most exponent of some constant absolute value of s, logarithm of absolute value of s, when, say, absolute value of s is at least 2. Okay? This last statement is actually kind of trivial because you can prove it in the plane sigma greater than 1/2, right? Due to functional equation, it is enough to prove this when sigma is greater than 1/2. So if sigma is greater than 1/2, then absolute value of zeta of s is of order at most s, which is easily seen from the integral for zeta function. We proved it. We have s, integral of fractional part, and so on and so on. And absolute value of s minus 1 is also at most absolute value of s squared. Pi to the minus half is of order at most, say, exponent of absolute value of s, which is a very rough estimate. And one can prove that gamma function, well, absolute value of gamma function is, say, at most integer part of absolute value of s plus 1 factorial, okay? And factorial grows at most like s to the s, and so you get s to the s here, okay? Nice. What can we do? Wait, this is of course. It's okay because I assumed that absolute value is at least 2. Okay, so this function is of order at most 1, right? If you substitute this estimate here, you get that psi is of order at most 1. Right? Because logarithm grows roughly linearly up to some logarithms, which we do not care about. But also, zeros of psi1 are the same as non-trivial zeros of zeta of s, right? Why is that so? For sure, if zeta of s is equal to 0, then psi of s is also equal to 0, right? If your 0 is non-trivial. And if it is trivial, then it is cancelled out by the pole of gamma. Correct? Okay. So zeros of psi1 are non-trivial zeros of zeta. This means that by lemma, psi1 of s is equal to exponent of a plus bs for some a and b, and then product over all rho 1 minus s over rho e to the power s over rho, right?
This is by Weierstrass one.
Yeah, correct. This is due to Weierstrass
То
factorization.
есть это мы сейчас теорему доказали.
Нет, это я сейчас просто разложил. Мы пока доказываем теорему, мы в процессе. So psi1 can be expanded into the product over zeros, but you can actually replace this by the following: e to the a plus b1 as product with star. I will explain what is the product with star. 1 minus s over rho. So I can get rid of this exponent. And what I mean is, if you group together rho and rho bar,
Сейчас, там B1S.
B1, другая константа.
So, осталось 7.
Осталось тем же. So if you group together rho and rho bar, two conjugate values, then you get what? You get double real part of rho divided by absolute value of rho squared, right? So this means that the sum over all rho, 1 over rho plus 1 over rho bar, is less than infinity. So if you group together conjugated zeros, then you get an absolutely convergent series. Correct? So this product will be the symmetric product. So you take you take all the zeros up to some quantity n, and then you take all the products, all the zeros from minus n to n, and all the zeros with opposite imaginary parts will cancel each other out, and then you get some constant out of these exponents, and also you get rid of the exponent in the product. Okay?
Сейчас, еще раз.
Еще раз,
Получается, вот
по-русски,
от-
значит.
От минус n до n, это вот мы что взяли?
Это вот как с
Минус- да, минус n.
несобственными интегралами. Иногда бывает, что сам интеграл расходится.
Вопрос скорее в том, у нас минус n и n это кто вообще на...
В смысле, ну что такое бесконечное произведение? Бесконечное произведение — это предел конечных произведений.
Да.
Я говорю, что нужно брать не...
Ну, у нас же s комплексная.
Ну и что? Произведение — это по ро.
Хорошо, ро тоже комплексная.
Ро — это счетное множество.
Ну,
это произведение по счетному множеству.
Ро тоже комплексное, вопрос скорее в другом. То есть вот у нас мы от минус n до n, то есть я пытаюсь понять просто как это...
От плоскости вот так отсечем.
Все,
мнимой части.
То есть это мнимая часть от минус n до n.
Да,
Все.
мнимая часть от минус n до n, и дальше n устремляем к бесконечности.
Pi with the star is we take
So
pairs.
this is equal to limit over n going to plus infinity, product over all rho, such that imaginary part of rho is at most n. 1 minus s over rho. And by this argument, this product actually converges.
Не, вот меня как раз таки интересовало именно...
Что по мнимой части?
Да, то есть это по мнимой части или мы откуда-то вообще непонятно?
По мнимой. Окей. So we take a symmetric product and we get a symmetric formula. Okay, so what do we
Сейчас,
do
а куда у
next?
нас экспонента исчезла?
Вот в этом-то и
Она исчезла как раз таки вот в это самое B1. B1 вот это самое. Все.
exponent is gone here because we can use the absolute convergence to get it out of the product. Okay? Any questions about this?
Why the conjugate of any conjugate of zeta function is also
Conjugate of zero of zeta function because this is an easy exercise, okay? Please prove that zeta of s conjugate is equal to zeta of s, okay? All the Taylor coefficients, say at 1 are real, so you get what you get. Okay, so now let us finally prove something. Lemma 2. Lemma 2 is as follows. Suppose that t is greater than or equal to, say, 2, and that's it, okay. Then you have the following. Sum over all zeros row, 1 over 1 plus t minus gamma squared, where rho is equal to beta plus I gamma, is at most logarithm of t. So this is a strange quantity here, but I will explain. Okay, so if you take non-trivial zeros of zeta, all of them, and then you sum the following quantity, 1 over 1 plus t minus gamma squared, where gamma is the imaginary part. Then the sum is not only convergent, it is actually bounded by logarithm of t. So there are not many zeros around t. Well, this is the moral of this lemma. So how do we prove this? This is actually a very easy result. So psi1 of s is equal to all of this stuff, right? Then psi1 prime or psi1 of s is equal to, well, it is equal to 1 over s plus 1 over s minus 1 plus half gamma prime over gamma of half of s plus zeta prime over zeta of s. Correct? This is just an expansion of logarithmic derivative.
To the
Now-
left are xi's and to the right are zetas, right?
What?
On the left hand side there's
This
psi.
is psi and this is zeta.
Okay.
You can check it by the number
They're
of...
quite similar.
The number of singularities, right? At least two singularities means psi, and one singularity right here is theta. Okay. So what should we do next? Next, we will set S to be 2 plus IT, and we are going to prove some bounds. Well, 1 over S plus 1 over S minus 1 is, of course, equal to big O of 1. Right? I claim that zeta prime over zeta of S is also equal to big O of 1. How do we prove this? Well, minus zeta prime over zeta of S, we know what this is. This is some Dirichlet series. Can you please recall what is the Dirichlet series for minus zeta prime over zeta? Логарифмическая производная зета функции. Монголия. This is the sum over all n, lambda of n divided by n to the s. Correct? And the series here is absolutely convergent. Well,
Это у нас был
lambda
вроде...
convolved with 1 is equal to logarithm. This is proved from the main theorem of arithmetics, right? So the generating function for this multiplied by generating function for this is the generating function for this, right? This is generating function for lambda, this is zeta, and this is minus zeta prime. That's it. Okay, so absolute value of this is at most sum over all n, lambda of n divided by n squared, which is big O of 1. This is just constant, right? So your series is absolutely convergent and everything is nice, right? Okay, so what do we need to deal with here? Maybe I will talk a little bit more than an hour and 20 minutes. I hope it's okay and nobody is too tired yet. Okay, so
No, I don't give this demo to what is.
we are proving it now. Okay, so we estimated zeta prime of zeta. Now we need to estimate gamma prime over gamma. I will prove a general estimate for gamma prime over gamma. So gamma of s is actually equal to e to the gamma s. Sorry, I don't remember exactly. Maybe minus gamma s over s, product over all n, 1 plus s over n, e to the minus 1 e s over n. This formula, by the way, also follows from Weierstrass factorization theorem. This is an exercise for you. Okay. Also, this can be proved. Oh, whoops. This is not what I wanted. This can be deduced from the integral like this. So t to the s minus 1 dt is approximately integral from 0 to n, 1 minus t over n to the n, t to the s minus 1 dt. This is a hint for the proof of this theorem without the Weierstrass factorization. Okay, so suppose that s is equal to sigma plus it, as usual, and suppose that absolute value of t is at least 2, okay? Or something funny like sigma is say no, I don't want to state the exact thing I would like to do here. Oh. Oops.
Пластик есть внизу.
Okay. Вот он пластик, да. So I don't want to state the exact statement here. So assume that absolute value of t is at least 2. Then gamma prime over gamma of s is equal to 1 over s minus sum over n minus. Is it minus or plus? I think it's minus 1 over n minus 1 over no, plus 1 over s plus n. Okay? Like this. Assume also that sigma is greater than minus some constant.
We took the logarithm and then took the derivative, right?
Yeah. And I also missed minus gamma. Yeah, you take the logarithmic derivative, which is the sum of logarithmic derivatives of factors. So this will be big O of 1, this will be big O of 1, and to deal with this sum, you sum first over all n less than or equal to, this is big O of, sum over all n less than or equal to your t, 1 over n, every summand here is big O of 1 over n, right? And then sum over all n greater than t, absolute value of s divided by n squared. Where does this come from? Well, 1 over s minus 1 over s plus n is equal to to s over n, s plus n. And this is at most absolute value of s divided by n, s plus n, right?
Is not minus.
Which thing is not minus? Ah, here you should also have minus. Correct. Right? Is this understandable? Is this correct? So what I want to do is to state that gamma prime over gamma of s is at most logarithm without a square of t. So logarithmic derivative of gamma function grows at most logarithmically when your imaginary part grows. Okay? Правдоподобно?
Ну, вроде пока что не очень видно.
Значит, еще раз. Есть сумма по n не очень большим,
И
есть сумма по n очень большим.
Ну да, по n очень большим сходятся, очевидно.
По n очень большим не больше логарифма, здесь сходится и оценка модуля s поделить на t. Но модуль s поделить на t это оба
Явно меньше логарифма.
Вот, явно меньше логарифма, да. Okay, so substituting everything we got here, we obtain that psi1 prime over psi1 of 2 plus it is of order at most logarithm t, right? Correct? I hope so. Okay, now this is equal to the sum over all rho 1 minus s minus rho with the star, I mean symmetric sum, plus big O of 1. So this symmetric sum is at most logarithm. Correct? Now let's take real part. Real part of 1 over s minus rho is equal to what? 2 minus beta divided by 2 minus beta squared plus t minus gamma squared, where rho is equal to beta plus I gamma. So 2 minus beta is at least 1 and at most 2, because our zero should lie inside the critical stream. So this is this is at least 1 over 4 plus t minus gamma squared. So this sum 1 over 4 plus t minus gamma squared is at most logarithm. So the sum with 1 will also be at most logarithm, of course. 1 over 4 plus x squared and 1 over 1 plus n squared are, well, they bound each other, right? So this is of order 1 over 1 plus t minus gamma squared. And this concludes the proof of lemma. And let us derive, well, I will state two easy corollaries. First corollary is that the number of rho such that absolute value of gamma is at least t minus gamma, t minus 1 and at most t plus 1 is at most logarithm of t. Well, of course, because the contribution to this sum of every such row is at least 1/2. And so the total number is at most logarithm. And the second corollary is that the sum over all rho such that absolute value of t minus gamma is greater than 1 over t minus gamma squared is at most logarithm of t, once again. So there are not too many zeros of zeta around any point. Okay, so I guess I've run out of time, but I would like to state the third lemma here. Let me state the third lemma without proving. I will prove it next time. So if sigma is greater than, say, greater than or equal to minus half and less than or equal to 2, then zeta prime over zeta of sigma plus it is equal to sum over all rho, 1 over s minus rho, plus big O of logarithm of t. This result is, well, in absolute value of t is at least 2, once again. This result is obtained easily by the same means. You need to take a derivative of psi function and then use some tricks. Okay, so this will be proved next time. And let me finally prove the explicit formula. Okay, this will be a big, how to say it, maybe something like big major chord here. big nice note at the end. Proof of theorem 2 will be as follows. So take t1 greater than t and less than or equal to t plus 1 such that absolute value of t minus gamma is always at least 1 over log t. So there are not too many zeros around any number. So inside any interval of length 1, you can choose a point which is far enough from any imaginary part of 0 of zeta. Okay? Then Perron's formula says that psi of x, this is by theorem 1, psi of x is equal to 1 over 2 pi I integral from b minus it to b plus it minus zeta prime over zeta of s, x to the s over s, ds plus some remainder term. Right? This is due to Perron's formula. And let us also fix b to be 1 plus 1 over log x. This will be convenient. Now, we need to decide some stuff. First of all, what is the bound for lambda of n? How can we choose a here? What is the obvious bound for the Mangold function?
Logarithm.
Logarithm, correct. Take a of x to be logarithm of x. Next, what is alpha? Alpha, let me remind you, is that absolute value of logarithm of lambda, sorry, divided by n to the s should be less in order than 1 over to sigma, sorry, 1 over sigma minus 1 to the alpha. So what is the value of alpha here? So this is just minus zeta prime over zeta of sigma. And zeta has a simple pole at 1. So alpha should be equal to 1. Right? Zeta prime has pole of order 2, and zeta has pole of order 1. And then we get this, right? So we can write an estimate for R. R is big O of x to the b divided by t b minus 1 plus x log 2x, which is the same as log x, divided by t. Log x squared, sorry. Because we have another logarithm in the theorem. So we get this. X to the b is the same as ex, so this is big O of x. So R is actually x log squared x over t. Correct?
Сейчас, еще раз, можно, вот почему мы это срезали x в бетой?
Еще раз. x to the b is equal to x plus x to the power of 1 plus log x, which is x multiplied by e. So it is big O of x, for sure. Right? Okay, so now we get that psi of x is equal to 1 over 2 pi I integral plus big O of what we wanted. Right? Now we need to deal with the integral. And we are going to deal with the integral in a very funny way. So first of all, we don't need to integrate to t, we need to integrate to t1. This is a simple technical problem here. But then we are going to deal with it as follows. So we are going to once again shift the contour to the following: minus 1/2 plus IT1 minus 1/2 minus IT1. And we are going to complete the contour. Okay? Let us denote this contour by C, and then from my exhausted listeners, I want to hear an answer to the last question. What is the integral 1 over 2 pi I integral over C minus zeta prime over zeta of s x to the s over s ds?
The residue.
This is the sum of residues. And what are the residues? Where are the poles of this expression? Non-trivial zeros of zeta, and also one pole of zeta, and also 0. 0 will contribute almost nothing, so this is equal to x, which is when s is equal to 1, you get 1 over s minus 1, and then you get x. Then you have sum over all rho, such that imaginary part of rho is at most t1, x to the rho over rho. This is because whatever multiplicity of 0 you have, your logarithmic derivative will always have a simple 0, right? To demonstrate this, assume that zeta of s is approximately s minus rho to the m, then minus zeta prime over zeta of s will be approximately minus m over s minus rho. This is also a reason why we should count zeros with multiplicity, because multiplicity is here in the numerator, right? So we get this, and then we need to estimate the remaining integrals. Estimating the remaining integrals is not very hard. So here you have integral of length t1, and your function under the integral is at most logarithm of x divided by square root of x. Okay? And you also have 1 over absolute value of s. So this last integral is bounded by logarithm x squared divided by square root of x. Okay? And then on the top and the bottom of your contour, you have these two integrals, and here on the top, zeta prime over zeta of s will be bounded from above by logarithm squared. This is due to our choice of t. I will probably explain this in a little bit more detail next time. So we have this bound, and then you have also x to the b, the bound for x to the s, and 1 over t, the bound for s here. And so you get a bound x to the b logarithm squared x divided by t. And x to the b is ex, so you get the same error term. So this concludes the proof of explicit formula, and I have negative amount of time, so I will continue next time speaking about the explicit formula, and we are going to finally derive the prime number theorem. But I also have an announcement that next time the class will be online, once again due to conferences. But this means that I will write everything down before the lecture, and so we will have lots of formulas to discuss. Okay, so I hope I at least convinced you that the explicit formula is true, and so proved that there is a relation between the distribution of psi of x and the distribution of zeros of zeta. And that's it, I guess. Thank you very much. Так, все, я останавливаю, да? I guess. Thank you very much.
Do you remember what is this psi Chebyshev function?
It's a sum of manifold functions.
Yes, it's some manifold function. And also there is Chebyshev theta function. Power. Sorry. Yeah, theta. Which is sum of logarithms over primes, less or equal than x. And you know that their difference is small, yes? Because this is sum, this is theta of x plus theta of square root of x. So the difference is what? Big O of what?
Theta of square root of x plus theta of...
No. Square root of x, I think, is enough, because here plus big O of this, yes? Because you have no more than here big O of logarithm x sums, and this sequence decrease. And this is big O square root of x. So we can find asymptotic formula for theta function. It's the same. And for example, you know that theta of x is asymptotically equal to x, that it is x plus some small function. Then what is pi of x? It is integral from 2 to minus, I mean that 2 minus epsilon, when you take the limit up to x of what? D theta of x over logarithm t, and here t, okay? And theta is such sum. So this is integral to x dt over log t plus d r of x over log t. Now you have such what's
Where does this equation on pi of x come from?
by definition. Pi of x is number of prime less than x. And this function is sum of logarithms.
Okay.
So
Yes, I hear.
here, if we integrate by parts, we get here is t, r of x over log x, yes, plus integral of r of t t logarithm square, yes? If r of x is small o of x, this is small o of x over log x. This is small o of actually of x over logarithm square. We see that actually this r of x, it is, for example, by Riemann conjecture, it is hypothesis.
We integrated by parts here, right?
Yes, yes. It is because of square root of x logarithm square.
Сейчас. Извините, два минуса это у нас... Можете вот просто пояснить это значение? 2 минус эпсилон какое-то.
2 minus epsilon, and after that we take the limit epsilon to 0.
Да, ну все.
And we will prove, for example, I think on the next lecture, that this is because of x exponent of some constant square root of logarithm x.
Spoilers.
Yeah, spoilers. So this is, of course, this is small o of x over logarithm square. And let us compute this integral. It is denoted by Li of x integral logarithm.
Logarithmic integral.
Logarithmic integral, yes. We have integral from 2 to x over logarithm t. If we integrate it by parts, what we get? X over log x, yes, plus I think integral from 2 to x dt over logarithm square. Minus plus big of 1. Such way. I mean, at 2, it's 1 over logarithm 2. Doesn't matter. Okay, this is integration.
So d of x is usually from
1 to x, right?
Small d of x is from 0, yes? Oi, from
What?
Li of x is what does it define? Small. Li of x, it's integral from what? From 0.
From 0 to x.
And at 1 you should take 1 plus epsilon, 1 minus epsilon, and when epsilon tends to 0.
Sure.
They are different by some constant. And what's this integral? Again, we can integrate it by parts, and we get x over logarithm square x plus 2 integral from 2 to x 1 over t over logarithm t to the power 3. And so we see that phi of x is x over logarithm x, but knowing that this r of x is small from the future theorem, we can write that this is x over log x plus x over logarithm square x. And next will be plus 2x over logarithm x to the power 3. Next will be 6, so 3 factorial, etc. Here I will write small o of x over logarithm to the power 3. So I want to say that This integral logarithm, it is phi of x more precisely than x over logarithm x. And okay. Now we switch. Of course, in other direction it's easy also in same way. Problem B. Prove such formula. I think.
Сейчас еще раз можно вот
Ага.
концовку? У нас получилось, что p от x это x log, ну, x делить на log, плюс
Да.
x делить на log квадрат, плюс 2x делить на log куб.
Да, там будет даже 3 факториал. X
И
на
получается,
логарифм.
что
ну,
x делить на log квадрат это почти константа у нас, или что?
Нет, она мало от x делить на логарифм.
Нет, почему у нас это получилось, что... Еще раз.
Ну,
У нас... все.
я хотел сказать, что вот этот r от x, он на самом деле очень, он маленький. И он меньше, чем x делить на логарифм любой степени. И на самом деле у p от x есть вот такое разложение. И ее интегральный логарифм более точно приближает, чем, конечно, два частных разложения.
Ладно.
Next problem. Prove such formula. Logarithmic derivative minus logarithmic derivative of zeta function is s over s minus 1 plus s multiplied by integral from 1 to infinity psi of x minus x over x to the power s plus 1 dx. I think someone can do this. First of all, what is this sum?
We were given in the lecture that it can be as a direct series. It can be
Yes,
expanded
this
as,
series of what?
as Mangold function and
One.
then divided by to the power of s.
This is for real part of s greater than 1. Okay, now we can write this as an integral. Which integral?
Тут не может быстрее получиться через двойственность преобразования Фурье. Ну, который вот не преобразование Фурье, а вот
Мелина?
Мелин трансформ.
Понятно, что это оно, но давайте все-таки по-честному напишем. Он не любит это.
Ну, например, у нас 52 должна быть, да? Я почему-то...
Нет, там единица.
Единица? Ну, может быть, да, единица. Тогда здесь, when we write here, integral from 1 to infinity. Вот. We don't need any theorems here, just by definition. Does everybody know what is Stiltius integral?
Кого?
Stiltius.
Суммирование по частям делаем.
Ну, знакомы с интегралом Stiltius? Или кто не знаком? Who does not know Stiltius integral? Okay, let me remind you that. If you integrate function from a to b, f of x dx, just usual Riemann integral. You have your function, and when you do some partition of your integral, yes, and you sum f of psi I multiplied by this will be, for example, ci plus 1 minus ci, yes? And you sum it all, it's the usual definition of Riemann integral. And then you take the limit when these partitions were maximum length of such small partition tends to 0. And now, what is integral from a to b f of x d g of x? This is just integral. We have some restrictions on g, but we don't think about it now. And it will be such sum g of I plus 1 minus g of ci. Okay, and the same limit. For example, if g is differentiable, then you can write this as g derivative at some point in this small interval multiplied by ci plus 1 minus ci. And you see that this is equal then to integral x dx, yes? But if your function is not integral, for example, our function is psi of x. Psi of x, your function is like that, yes? So these differences, they are 0 unless you are in some neighborhood of integer of in some neighborhood of a power of prime, yes? And then this difference is equal to Mangold function, yes? And so here it will be d psi of x, and but this difference is equal to yes, to lambda of n, and you should divide it by x to the power s to get this. It will be and it will be the sum. And what's important about Stieltjes integral that we have integration by parts. We have such formula that this is f of x, g of x from minus usual integration by parts, but more general because it's still yes integral. And for example, maybe you know Abel summation formula, it's a particular case of integration by parts in this context. Okay, let us continue. We write it in such a way. Now I think we should integrate by parts, yes. What we'll get?
Да, ну это будет, получается, вся ты здесь на степени, на их степени s.
From infinity to 1.
От единицы до бесконечности.
Yes. And here we assume that real part of s is greater than 1. Minus 1.
Интеграл от единицы до бесконечности.
Да, интеграл от единицы до бесконечности. Как раз таки минус s делить на x в степени s. Сейчас. Все от
Plus s, yes, because minus s, psi of x over what?
На x в степени s плюс 1.
Dx. Yes, here we used that function x to the power minus s is differentiable and used this observation. Okay. What's this?
Ну, бесконечность 0 получается.
Yes, 0 at infinity.
Единица это будет пси от единицы.
Psi of 0, of 1 is 0 also.
Ну, значит 0.
Uh-huh. 0, so we get such formula. And now, but in our exercise, we have psi of x minus x. So, if we write here minus x, we should sum it with s, integral from 1 to infinity, dx over x to the power s. And this is
То... Да, понятно почему.
I think now, yes, this is exactly s over s minus 1. So we proved our formula. Now, I want to prove that prime number theorem, what's prime number theorem? With,
And does it mean
huh?
that we have psi x minus x plus this, not just psi x over this? Or does it mean?
So psi of x is close to x. So this formula is not true. For example, when s well, it is true, but if you integrate with psi of x instead of psi of x minus x, then the integral will not be convergent if in some for some cases, say this is more convergent than integral than what you proposed.
Yes, but assume that psi of x is x plus small o of x. Why? I want to prove that when zeta function has zeros on the line.
This is 1c.
Yes, it's 1c. Assume that zeta function has such zero. What can be said about logarithmic derivative at this point? What it will be?
We have a pole.
Yes, we have a pole. And so if we write sigma plus it, then we expect that our logarithmic derivative it will behave like what?
Why are you sure that the derivative, that it will be positive, that there will be no zero of the zeta prime?
There will be, but with a smaller order.
What's the question again, sir?
Okay. That's obvious.
Hmm?
I understand. Yeah. That's obvious.
So what it will behave if we assume that zeta of 1 plus it is 0, and if we take this t0 denoted, and what it will behave if sigma is small? It will behave like
If sigma is small, like... Сейчас, а может мы сигму к единице устремим или что?
Okay, yes. Yes, sigma to 1. 1 plus, yes. It will behave like some constant divided by sigma minus 1 to the power k. If the k...
Из того, да.
No. It will be just a over
Sigma minus 1.
Yes, because we have because this is logarithmic. And what's the contradiction? Now look at this formula.
So this is because it will have a pole in this.
Yes, because it will have a pole, yes. And what's the contradiction now?
This has to contradict prime number theorem.
It has to contradict, yes, that this is small o of x. We have such integral, yes, s, which tends to let us consider such integral. Small o of x over x is plus 1 dx. This is integral. Small o of 1 is over x is dx. dx sigma. Okay? Because we take modular. I mean, here I think yes.
What is this integral? It's from.
Yes, it's this integral. This tends to constants. And what is integral? 1 x to the power minus sigma, it is integral from 1 to infinity dx over x over sigma is what? It is 1 over sigma minus 1, yes? And if we have small o of 1 in this integral will be small o of such integral, yes? This is the contradiction.
Well, this is not immediately obvious, right? Because small o is for x goes to infinity.
Yes, and so we should divide this into integral from 1 to some big n, from n to infinity, and for example, this small o of 1 is less than epsilon, then x is bigger than n. Yes, but I think you understand. Yes?
So we have minus theta prime divided by theta is s divided by s minus 1. Like, where did all the s go?
Huh?
Where did the s go in this formula?
S goes to 1 plus
Some it.
IT0, yes. We know that at 1 it is equal to, we don't need to check this. T0 is not 0.
S is bounded.
Okay, so okay.
S is sigma plus IT.
IT0, yes.
So we just ignore this it and all of these constants.
Because IT is bounded.
Well, okay.
You mean here?
Yes.
Yes, it is fixed. IT is fixed. I think if you know something like, I'm not sure, no? If you know that psi of x is less than 2 minus epsilon x, for x large enough, I think from here you can deduce that your 0 cannot be double 0. So it must be simple 0. Yes. From but in exercise 2 we will deduce in another simple way. First of all, y is zeta of s modulo to power minus 1, y it is less or equal than zeta of sigma.
Сейчас. Мы вторую только что вот разобрали.
Ну, вторую я сказал, что, видимо, если вот из этого же рассуждения с интегралом мы видим, что если пси от x там меньше, чем 2 на x, еще минус что-то, то у нас вот здесь вот не может стоять двойки, а здесь стоит кратность нуля.
Понятно.
Ну, я говорю, что можно полегче делать, вот как вторую сейчас поймем, очень просто. Who knows how to prove this inequality? I think we proved it on the previous seminar.
Сейчас. А это вот к какой задаче относится?
Это следующее. It's
Больше единицы.
two. exercise 2.
Сигма больше единицы.
Yes, of course, sigma is bigger than 1.
Блин, это такая. Всё.
Вот свидетель Хейсерис по зит это выполнено minus 1.
Сумма, ну вот на прошлом семинаре мы писали, z минус 1s равняется сумма μ от n, деленная на n в степени s.
And mu of n is a modulus function. It is 0, 1, or minus 1.
Дальше просто модули ставим.
Ага.
Мы говорим, что это будет больше равно чем. Можно, да, средних сумму модулей. Это я сумму просто единица, а n
n степени сигма.
Да, даже получается, можно чуть получше написать, чем z от сигма.
Ну да. Okay, and how to prove that zeta cannot have not if zeta has a zero somewhere, that it must be simple.
We're still proving this inequality. Oh,
Hmm?
no, we proved it.
We already proved it.
Well, I
Yes.
looked at it.
Are there any questions about the proof?
Это про то, что у нас не все нули на сигма равны единице простые должны быть. Мы это только что.
Ну, их вообще нет, ну да, но мы сейчас
Ну.
простые должны быть.
Если 0 хотя бы второй степени, то у z в минус первой полюс хотя бы второй степени. Ну, возьмем тогда вот, допустим, последовательность. Ну, последовательность там, допустим, сигма, которая стремится к нулю, и их всех плюс эту мнимую часть. С какого-то момента на ни квадрат.
Да, здесь я неправильно тогда эти 0, здесь я... Ага. То есть что?
Сигма стремятся к единице, допустим, справа. И s это все они
So
плюс.
when sigma tends to 1 plus, if zeta has a 0, this will be zeta 1 will be some constant multiplied by sigma minus 1 to the power k. And here we know that zeta has a simple pole at 1. So this will be 1 over sigma minus 1. And we will have contradiction.
Didn't we just prove that?
Oh, here it should be
Минус первый.
minus 1, yes. And we will have contradiction if k is bigger than 1.
Didn't we prove in 1c that it can't have zeros?
No, how?
Well,
A can be small.
Сейчас, откуда мы получили оценку на z от сигма?
Z от сигма, ну, мы знаем, что у z полюс в единице.
Да.
Значит, в единицу у нее какое разложение в ряд? 1 на s минус 1 плюс константа плюс большой это ряд этого.
Сейчас у z
Варано.
от s в минус первый полюс в единице.
Z от s вот.
А,
z от s, sure.
Нет полюса, там
Вот. This is Taylor expansion at 1, and from this we know this fact.
Мгм. Так, все, да, понятно.
Как докажем, что нет?
well, 1c says that zeta of s has no zeros on the line s equals.
Has no 2. number 2 says that it must be simple zero if it has zeros. And 1c, we prove that there is no zeros, but if we know prime number theorem.
And we don't know.
Yes, and we don't know prime number theorem, actually it is equivalent. So let me say a few words about this. Okay, actually this is equal prime number theorem, and is equal to zero has no zeros. S is 1 plus 90. And we proved in this direction. Last two exercises are about Newman's proof in other direction. But there are different ways to do it. On the I'm not sure that we will have time for last two exercises. On the lecture you proved Perron's formula. Yes?
Это к какой задаче сейчас просто прокачать материал?
Ну, сейчас я просто хотел прокомментировать, что
Да.
вот это два эквивалентно. И что в последнем 6 и 7 это доказательство в другую сторону Ньюмана.
Понял.
On the lecture you proved such formula that psi of x is equal to the 1 over 2 pi I integral in some constant minus t plus t, and here it will be x to the power s over s and minus derivative of zeta function plus some remaining term which is small. And you see, you have integral over such contour. Yes. When you have it, you want to compute it, and how you compute integral over contour? For example, you can shift it. If you know some zero-free regions here, that you don't have zeros here, you see zeros of zeta are the poles of such functions, so you can move it in this zero-free region. Yes? And on this line, you have x to the power s, x to the power s will be small. Okay, and that's the point that zero-free regions gives us better and better remainder term in our problem. So when you prove that psi of x is x plus L of x is better when you have some zero-free regions. And Riemann hypothesis says that you don't have zeros, you have only zeros on this line. So you can shift this contour up to 1/2, and there x to the power s will be x to the power 1/2. Okay, but another tactic that you made on lecture is to shift this contour far, far away to the left. And then you will have a sum over zeros. And again, you see that smaller the real part of zeros is, smaller this remaining term is. But there is a problem to shift it on this line. I think it will, from Perron's formula, it is not clear. I mean, how to do in this direction, but you see there is a relation between absence of zeros in some regions and this remainder term. Okay, now exercise number 3 is about Nava.
Can we go back? I'm sorry.
Huh?
This proof that if it has a zero, then it must be a simple. Could you repeat it quickly? Briefly.
Ага, так по-русски тогда. Вот мы поняли, что если у него не простой ноль, то вот так вот, где k больше.
Да. А дальше?
А это мы знаем, мы получаем, что там неважно, сигма минус 1 в k-той, что растет так же, как 1 на сигма минус 1. Но это неправда, если k не равно единице при любой константе.
Почему он должен расти как сигма минус 1? Просто появится определение.
Потому что меньше равно, да. Да, что это меньше равно. Вот это неправильно. Потому что это будет гораздо быстрее к бесконечности стремиться. This will tend to infinity much faster than this. This is sigma, and this is
А должно так расти, и получается противоречие, потому что z of s имеет такое разложение в единицы, да? Вот один
вот
разделить на
это, понятно вот это, что
Да.
вот это растет как
Ну да,
z от сигма. Это растет как z от s минус 1, если там.
Окей,
Ну, это, конечно, противоречие, потому что возьми, сигма маленькая к единице, вот это маленькое,
Да,
еще
да.
в степени минус k. Next exercise is about another proof. Is about a proof that zeta has no zeros on this line without using prime number theorem. First fact: logarithm of zeta of s is sum of primes 1 over p to the power s plus what? Plus some function that is regular for sigma greater than 1/2. How you can prove this? What's the series for Dirichlet series for logarithm of zeta function?
P here is 0.
Huh?
What
No, it is-
what is the summation over here? Just prime
Over primes,
over all primes?
yes. We made this exercise somehow this exercise on the very first seminar. So I want to say that logarithm of zeta of s is sum of primes, sum over n to infinity 1n s.
I already forgot what a regular function is.
What you forgot?
What is a regular function?
Regular. I want to say that it is, for example, holomorphic for sigma
Holomorphic just.
greater than 1/2. Yes, and also it is. I think it is also bounded for sigma greater than 1/2 plus epsilon. For every epsilon, we can give a bound in this region. You know why is this equality? Zeta of s is product over primes 1 s minus 1. So logarithm of zeta of s is sum over primes minus logarithm of 1 minus 1 over p to s. Yes? And then you just write a Taylor series for minus logarithm of 1 minus x. It is such sum.
Logarithm of zeta of s is sum over the same thing. Should be.
Yes, it's the
What?
same thing, minus here.
Okay. Yes, okay.
And you get immediately this formula,
Yes,
yes? And here we have such sum plus sum over powers of primes. And of course it diverges very well if s is bigger than 1/2. So that's the point. But here And what's the sum over p to the power sigma? It is asymptotically equal to logarithm over 1 sigma minus 1. I think maybe me, someone of you made this on our first seminar on the board. It's just logarithm of zeta behaves like that. And we have this sum, and f of s is it tends to constant, to some constant. So that's what. And if we have a zero, for example, zeta of 1 plus zero is 0, then we know that such sum, how it behaves when sigma tends to 1. It behaves like what? If zeta has a 0. Yes, like logarithm of sigma minus 1. And you see this is negative and tends to minus infinity, yes. Is it clear?
Откуда это?
You should have minus. So,
Where minus?
уже решение было 1, логарифм отделили на сигма минус s.
А здесь сигма минус 1. Это другая сумма. Это мы предположим, что 0. Здесь поле, здесь 0.
Откуда вы логарифм?
Да, я не прав, наверное, сейчас. I said that if zeta has a 0, then zeta of s is s at the 0. If we write Taylor expansion, it would be s minus 1 minus e t0 some constant a plus b s minus 1 minus a t0 square plus etc. Yes, that's the neighborhood of 1 plus e t0. And if we take logarithm of this, we get that logarithm of zeta of s in such neighborhood. It will be logarithm of a s minus 1 minus a t0 plus logarithm of some function like 1 plus some other constant s minus e t0 s minus 1 minus e t0 etc. This is logarithm of 1 plus. This is small. Yes? And this logarithm of a, it's a constant, and logarithm of s minus 1 minus et 0, it's logarithm of sigma minus 1. And it tends to minus infinity. And we have such asymptotic formula. If it was a pole, it will tend to logarithm of 1 sigma minus 1. Okay? Is it clear now?
Еще самый последний момент.
Ну, что именно?
Непосредственно откуда логарифм сигма минус 1 берется?
Ну, логарифм вот этого берем. Там у нас 0, и оно в окрестности ведет себя как а на сигма минус 1. Но если логарифм возьмем, оно в окрестности ведет себя как логарифм сигма минус 1, а логарифм в константу идет, ну, не важно. Да? Are there any questions about this important stuff?
Так вот, то что сумма 1 делить на p в степени сигма, это берется от логарифма, это будет на сигма. Это всегда или в полюсе трика?
Если if this is 0, нет, no, there is only one pole, we know. Zeta has only one pole at 1. Here we know that it is a pole, and from this we deduce such asymptotic. And if it has 0, we want to prove that it can hold. Then we have such asymptotic formula. Do you understand why? Точно?
Ну, типа, из того, что
Ну, там сигма минус 1 будет как, да, главная часть. Ну, там а на сигма минус 1, но если логарифм взять, то просто сигма минус 1.
так, а вот эти две формы, они не противоречат друг другу?
Это в единице полюс, это где-то 0. Они не противоречат друг другу.
Короче, цвета рядом с нулем. Там
Сигма плюс и t0.
А, там за нулевой другой придется.
Yes. Here is t0 is 0. Here is some t0 that we assume is 1 plus t0 is 0.
Сейчас, если еще раз, у нас получается, вот мы взяли логарифм сумму сумм, дальше из нее вытащили для m равно единице все. Ну, то бишь 1 делить на p в степени s. И потом у нас как получилось, что...
Мы говорим, что...
То есть почему у нас вот остаток будет регулярен?
F от S почему будет
Да,
регулярным?
да.
Ну, это чуть-чуть до этого, да.
Да, потому что у нас получилось...
Потому что здесь сумма будет по степеням 1 делить на p в степени 2s.
А, ну
или
да,
даже
да,
3s.
конечно, конечно.
P в степени
там
2s, оно
найдется.
больше единицы, если s вещественная
Да,
часть.
понятно, хорошо, да, все.
Okay. And now let us write, think the, yes, it will be the real part. What's the real part of sum 1 over p to the power s? What is 1 over p to the power s? It is what? It is p to the power minus it over p to the power sigma. And this is exponent of minus it logarithm p over p to the power sigma. And this is what? This cosine of t logarithm p over p to the power sigma plus minus I sine t logarithm p over sigma. Yes? And if we compute real part, it's just such sum of yes, sum of t logarithm p to the power sigma. Sum of it. And here, what's this? This is real part of zeta of s, yes? Minus a real part of f of s. And what's of logarithm? Yes, it's important, of logarithm. And what's the real part of logarithm?
Сейчас, черт, там у нас получается делить на p в степени сигмы или что? Сейчас не так. У нас сигма это не так. S это сигма плюс t. Мы сейчас предполагаем.
S всегда сигма плюс t.
Хорошо, да. Просто мы в какой-то момент брали, что сигма у нас стремится. Ну, короче, сигма у нас другое обозначало, поэтому я на всякий случай уточняю.
Может, как обозначало?
Логарифм модуля.
It's a module,
Yes.
logarithm of module.
Yes, logarithm of module. Ага. Minus sum So we see, once again, the same. But let us assume that 1 plus e t0 is 0. Yes? When we have such, first of all, we have such sum, p to the power sigma over p. Second sum is it's called cosine t0 logarithm p to the power.
We're already doing C, right?
Ага.
Сейчас. Как мы B закончим тогда? Как-
Yeah, I thought we had to do something with real part of f of s.
Real part.
Well, okay, maybe it's not.
Чего? Сделать что?
We needed to finish B, right? 3B.
Yes, we finished the...
Сейчас, а как мы там получили, что у нас вот эта вот сумма эквивалентна, ну,
Логарифм от сигма минус 1?
да, у нас же там получилось...
It's modulo theta of s, so it's clear. Okay.
Okay, we'll do it now. Okay, we did a bit another, but doesn't... Now, yes, now I want to say this is real part, this is logarithm of module minus some good controllable function. And logarithm of module, yes, it will behave like logarithm of sigma minus 1. Yes? So this will behave, if sigma tends to 1 plus, it will behave like logarithm of sigma minus 1.
Сейчас еще раз, почему это... Просто можете, пожалуйста, повторить?
Ну, если вот z 0,
Да.
в 1 плюс это 0. Что если 1 чуть-чуть вправо, сигма плюс это 0?
Да.
То там будет, если на это 0 сдвинуть, там будет в единичке 0. Сигма минус 1 будет множитель, а дальше там сигма минус 1 в квадрате. Там константы какие будут, неважно. Логарифм берем, получается асимптотически как логарифм от сигма минус 1.
Угу.
Ага. This like logarithm of... Запись? And what's the idea? You see, this is this tends to minus infinity. Yes. This means that this cosine is very often it is close to minus 1. Yes, because these are different by their sign. Yes, знак. Here is 1, and here we expect this, that this is very often it is minus 1. But when let us consider such sum at the origin of 1 plus 2 it0. So here will be the sum of primes cosine over 2t0 logarithm p over p to the power sigma. If this is very often minus 1, then this is very often 1. So we expect, it is not proof yet, that this is behaves like logarithm of 1 over sigma minus 1. At least this tends to infinity. But it will give us that we have a pole at this point, 1 plus 2 it0, and we know that zeta function has only one pole. And this will give us a contradiction. So this is the idea, and the proof of, you know that prime number theorem was proved by Adamar and de la Vallée-Poussin in the same year independently. And Adamar's idea was like this. And he just finished the proof, so he made it precise. And it's not very hard, you can do it yourself, try to do it yourself, but here I present a slight another proof, it's variation of Adamar's proof by Atkinson. Let us prove such inequality. P square is less or equal than 1/2 of s plus q multiplied by s.
Do I understand it right that not only prime number theorem implies that z of s has no zeros and 1,
Yes.
but also the other way around?
Yes, the other way, and the other way was known before it was proved that there is no zeros. So to prove that there is no zeros, it was the last step in this theorem.
Okay.
Okay, I think you can prove such inequality by yourself. Let us. Okay. Let us write what's this inequality. It says that sum over p cosine t0 logarithm p to the power sigma square is less than equal than what is s plus q? It is cosine 2t0 logarithm p plus 1 over 2. Here will be sum over primes over p to the power sigma, and here is the sum 1 over p sigma. Do you agree with that? But this inequality is just like that. I rewrite it.
Ну, кажется...
Правда? Ну,
Да.
я их вместе переставил.
Ну, просто у нас получается тогда, вот, можем вспомнить школьную форму,
Ага.
это понижение степени, вроде она так называлась.
Ага.
То есть косинус квадрат x это, да, вот это вот счастье.
This cosine square. And so we want to prove that let me write it here, that here is the sum over primes cosine square t0 log p over p sigma multiplied by. And how to prove this inequality? That this is bigger or equal than this.
Очень напоминает это, КБШ.
Да, это оно и есть, ну как?
КБШ.
Да-да-да. Каши-Шварц inequality.
Нет слов.
Who can write exactly how to use Cauchy-Schwarz inequality here? Okay, yes, just this. So maybe you should rewrite it slightly that t0 log p over p sigma 1/2, 1 over p sigma 1/2, and then it's just yes, Cauchy-Schwarz inequality. Everybody know this inequality, isn't it?
Большая русская железная дорога.
And now, how to deduce the contradiction from this inequality? So we know that S is behaves like that. So this inequality what it implies that logarithm 1 over minus 1 square, it is less or equal than what? Less or equal than you should multiply it by 1 plus small o of 1. Okay. What? Here will be square, s square over 2 plus s cube over 2. S square over 2 behaves the same way, but divided by 2. Yes, yes. S square. Here is B square. So we see that this should behave as SQ should behave like logarithm should be bigger, yes? Logarithm of 1 over sigma minus 1 square divided, not divided.
Почему у нас квадратстве так идет? Там разве не логарифм сигмы минус 1?
Что еще? Какой идет?
Ну, b квадрат мы записали, что это логарифм
Да.
1 делить на сигма минус 1
Ну,
в квадрате.
логарифм сигма минус 1, они знаком же отличаются.
А, да.
And from here you see that Q is bigger than logarithm of 1 plus sigma minus 1. You can make this precise by writing 1 plus small of 1, yes, everywhere, but because it's not equal, but it tends to. But you see that, of course, Q cannot be Q tends to plus infinity, must tends at least to plus infinity. So our function at 1 plus 2 I t0, it cannot be regular, and also it cannot have a 0, because in this way this will tends to minus infinity. So there must be a pole, and this is a contradiction.
Сейчас. Еще раз концовку можно? У нас получается, если у нас там 0, то тогда вот эта часть куда улетает? В минус бесконечность?
Да, должно улетать к минус. Сейчас. К плюс бесконечности оно должно. Оно, если там где? Вот мы не знаем, что у нас.
Да, у нас получается вот логарифм будет улетать в минус бесконечность, получается.
Логарифм сигма минус 1 в минус,
нет.
а логарифм 1 делить на сигма минус 1 в плюс бесконечность.
Так, и в чем проблема у нас будет? В том, что...
В том, что у нас в точке вот это улетело в плюс бесконечность, в чем проблема? Потому что это вещественная часть z в точке 1 плюс 2 это 0. Мы ожидаем, что если там 0, оно к минус бесконечно идет, если там константа, но оно к константе стремится. А плюс бесконечно, значит там полюс, но это противоречие. Are there any other questions? Next, I think we will do the last exercise because we have 10 minutes. This is a remarkable proof of absence of zeros on this slide by Ingham, because this proof and proof by de Laval-Poussin, it is exercise number 5, it's variation of proof of de Laval-Poussin. It used some information about zeta function at point 1 plus 2 I t0, yes? But in exercise 4, we don't use this information, so it's somehow different. First of all, this is for A, it's a formula. I think Ramanujan had this formula, maybe someone else. Zeta of x. Sigma A of n is sum of d divided n, d to the power a. Such formula, I think I should write it, but let us not prove this formula. I just want, do you know the idea how you prove the formula of such type? I think such formula, you can have such formula on your exam at the end of this semester. It is very common in such course.
You need some sort of additivity.
You see, this function is multiplicative. Product of multiplicative functions is multiplicative. So here is the Dirichlet series of multiplicative function. So it has an Euler product. It can be written as product over primes. Yes. Do you remember this? Huh? This is product of. Let us write. This is.
По проявлению будет 1 плюс f от b делить на p s там, и так далее.
1 plus p to the power s. Here what will be? It will be 1 plus p to the power a, 1 plus p to the power b, yes? Plus, etc. Okay? And here it's also multiplicative. It is product over primes 1 minus p to the power plus b minus p, yes? Okay, something like that. So you should prove. А?
Много народу экспертный экзамен задают.
Да, думаю, все там, типа, Kalmynin любит много задач дать, и надо решить там немножко.
Своими записями же можно будет пользоваться?
Там, типа, на неделю.
После этих слов начался сущий кошмар.
Ну, не знаю, как в этом, но, скорее всего, так и будет.
Друга расскажешь?
Да.
Опыт прошлого года на теории было. Это очень страшно.
Now, how you prove such formula? You should prove this inequality for every prime number. That this is equal to this. And this is just about power series, equality of some power series.
Способа осмысления.
And yes, and how, when you want to prove this equality of power series, how you do this? And actually there is a way to do it in a good way. Here is a rational function. If you take z p to the power minus s, it's a rational function. And when you look at it like a sum of partial fraction, you take a partial fraction decomposition, ложение на простые дроби. It's a sum. And when ну а дальше вы просто смотрите на ряд, который получается для каждой дроби. When you will have
So we decompose every...
You will have such sum, like some constant, which depends on p over 1 minus p a z plus etc. It will be p a plus b a. And when this is a 1 plus p a z plus p 2a z square plus, and that's how you find these coefficients. So it is a work, but it is finite. And but let us not prove this formula now. Let us use it to deduce the absence of zeros. Let us take this formula if A is Ci, B is minus Ci, and C is real. What we will get?
We already proved it.
Yes, but there are different ways to do it, and maybe in some other situation when we want the same for for example, flame function or something like that, we can use something similar. I think it is good to have several proofs which use different elements. Do you agree with me?
I don't mind.
Uh-huh. What this formula gives us?
Zeta of s squared
Zeta of s
squared
and zeta of s
squared because
yes squared s minus ci plus ci over
zeta of 2s
2s is equal to what? Sum over n.
They will cancel each other then.
No.
Well, it's a bit.
Yes, but not cancel, but what? They are conjugate. They will be conjugate. Uh-huh. And when you multiply, you will get the square of the module.
So just the sum of d1, d2 were both.
I mean, here will be ci of n. Do you agree with me? Let's see. Ага, все.
Why is it going to be squared?
Потому что
Не сопряженные немножко. CI и минус CI сопряжены.
Они же в степенях.
Ну, эти два числа сопряжены. Ну, сопряжение, да. Сумма. At least these are positive. And assume that zeta of 1 plus ci is 0. Yes? Then, of course, zeta of minus ci is what? Also 0, yes?
Also, yes.
Also 0. And yes, and zeta, it has a pole at 1. And if s is 1, these are two zeros and it has double pole. This means that they cancel each out and this will be regular at 1.
But there's also the denominator.
Yes, and
but it doesn't matter. Okay, it's
yes,
just
and what's the pole of the denominator?
1/2.
What? No, zeta. You mean
Well,
zeta of minus
there
2?
will be no pole if s
There will be a
equals.
pole, but s will equals to
What do you?
minus 1, I think. Zeta of minus 2 is 0.
Zeta of minus 2 is 0.
So the nearest pole will be minus 1.
Then you-
Wait.
But why do we need the
1/2.
zeros? Why do we?
What would be 1/2?
1/2? Where? Here?
Yes.
No, it's going to be a pole, and we are
It will
looking
be a
for
pole, it will be a 0 of such function.
zeros.
Yes, let's denote f of s, and it's very well that you noticed that f of 1/2 is 0. So, this service, it gives us a function which is regular everywhere where s is bigger than minus 1. But if s is real, yes, then this sum is positive, and if we take s to be sigma, and if we sigma move to from 1 to minus 1, yes, sigma. I think if this diverges at some point, it gives us a contradiction because we know that our function is regular everywhere here. Yes? So this is an equality everywhere where this everywhere for s greater than minus 1.
Yes.
Еще раз, как мы получили
Теперь
минус единицу? У нас, получается, минус единица будет полюсу f от s, так?
Да.
Так.
Это ближайший полюс слева.
Потому что будет 0 в знаменателе.
Ага, да. Ну, это понятно.
ну,
А дальше,
смотрите,
дальше какое у нас рассуждение просто?
Ну, например, говорю, что вот дальше мы вот двигаемся по вещественной оси, и вот это всегда равно вот этому. Потому что если, как это может нарушиться, если это в какой-то момент бесконечность уйдет, правильно? Ну, оно не уходит в бесконечность, потому что это не уходит в бесконечность. Значит, просто равенство. Ну, противоречие как получить? How we get a contradiction? For example, look at f at 1/2. This is 0, so this must be converges to 0. But this
But it's
all
all
terms are
positive,
positive.
yes.
Yes, so it's a contradiction, obviously. Окей. Это столько. Просто жать здесь старт, да? Кнопку красную тоже.
Да. Нет, там наоборот, там кнопка справа должна быть, вроде бы, или нет? Сейчас, короче.
Ну, так, наверное, да?
Нет, там наоборот, там кнопка справа должна быть, вроде бы, или нет?